Good evening, everyone. First of all, I thank the committee of organization to give me this opportunity to present in this international conference. My name is Mohamed-Yasir Nour. I'm PhD student in University Morocco and French. Now I present you our work in subdivision scheme domain, which is subtitle Mixed Hyperbolic Trigonometric Non-Stationary Subdivision Scheme for Mesh of Arbitrary Topology. This work is mixed with professors Barrera Domingo, Abdullah Al-Mni, and Ahmed Zidna. The plan choosing during this presentation is as follow. First, I will start by motivation and objective. Afterward, I will give two fundamental example in subdivision scheme. The first one is in curve cases, which is chicken scheme, and the second one is surface subdivision scheme, which is Dot-Savant scheme. Then I move to our work, which is the mixed hyperbolic trigonometric subdivision scheme. I recall first the univariate case. Afterward, I present the bivariate schemes, which is the goal of this work. And finally, I conclude this presentation by a conclusion and future work. Now, let's move into the motivation and objective, and starting by motivation. So, in the application, especially in computer-aided design and computer-aided geometric design, we always need to a smooth curve from initial mesh. So the traditional method used in this domain or in computer-aided design is using no uniform irrational B-spline, which known by NURBS. But the NURBS has many problems, like it is unable to present exactly the trigonometric or the Lissachus catenary curve LX hyperbolic exactly, and also it are be complicated in the calculation of mask in the application. So recently appeared a novel notion which called the subdivision scheme. So the subdivision scheme is defined as a smooth curve of the limit sequence from successive refinement, which means we started by initial control polygonal or initial mesh. From this initial mesh, we apply successfully the subdivision scheme, or we repeat much of time this subdivision schemes to arrive finally to a smooth curve or a smooth surface. And the application of this subdivision scheme is so easy because it's not complicated like the nerves. It's only really only need to control polygonal, which is in form of vector, and the subdivision scheme, which is in form of matrix, and apply this matrix or the subdivision scheme more of time to arrive finally to a limit curve or surface. This is other examples of application of subdivision scheme Like here we install by initial mesh of cars, and by apply 3 times this the subdivision scheme, we arrive to finally to these smooth cars. And the subdivision scheme, it is applicable and much of domains, and it's applied the first time to smooth the hand greases, like that. So here we have initial head which is not smooth. By application of subdivision schemes, we arrive to a smooth hand, and afterward it's applied the first time in games by NVIDIA cards to smooth cartoonage, animation, etc. Now let's see our objective and this work. So in this work we will extend our univariate MSE subdivision scheme to surface case. Secondly, we studying the conversion smoothness of this initial scheme and give a numerical example to show the performance of this new scheme. Now let's move into the known examples of subdivision scheme in the literature, starting by subdivision curve, which is the example of chicken scheme. So the chicken scheme, it is repeated stationary subdivision scheme, which is calculate the even point by application this formula to the old vertex, and the even point gauged by application of this formula to the old point. Like here in this example, we have this control mesh. By applying the chicken scheme, we have a new mesh which is in view bullet. This is scheme, and by reapplication of this chicken scheme many times, we arrive to these smooth curves. Now let's move into the subdivision surface, or the example of Dot-Sabin scheme. So Dot-Sabin scheme, it is a generalization of B-quadratic B-spline. So it is dual approximation because it is starting by browsing the faces, nor the vertices, like the Cashmore-Clark scheme, and applied to polygonal mesh. It generates a G1 continuous limit surface, which means C0 for the set of finish extra points, and C1 continues everywhere else. And now it's how it works, Dot-Sabin scheme. So Dot-Sabin scheme, it started by initial mesh D1, D2, D3, D4, D5, D6, D7, D8, D9. So this is the initial mesh. So the first step of Dot-Sabin scheme is calculate the middle age of each edge, which we denoted by E1, E2, E3, E4, etc. And afterward, calculate the centroid of each face, which is denoted by V1, V2, V3, and V4. And the last step, it is this formula. It is calculate the centroid of the faces containing the edge point, the face point, and the old point. So by calculating all these new points, we connect between them to arrive to a new mesh. This Dosavant scheme can be expressed in matrix formula. By that, for the regular mesh, we have this that's gated by the transfer product of chicken scheme or the quartic B-spline, and that can be expressed as follow. For the irregular mesh, so we can express it the Dosavant subdivision matrix like this. And application of this Dosavant is, as you say, that here we have the initial mesh. By application the first time of Dosavant, we get this new mesh, and by repeating this Dosavant scheme, we arrive to this smooth mesh. This is another example. We started from monkey initial mesh, and by repeating the Dosavant scheme 3 times, we arrive to smooth mesh. Now let's move into our mixed hyperbolic trigonometric sign. And I start by univariate case that I make in our previous work. So the mixed hyperbolic trigonometric scheme, it is a scheme that's expressed as follow, where C, D, K, L is a mask of subdivision scheme. Another thing that this mask is depending to level subdivision, which is K. So this scheme, it is not stationary, not like the chicken scheme, it is stationary, because the stationary scheme, it used the same mask for all level step of subdivision scheme, but in our case we have non-stationary, so it's depending to the level of subdivision. Another thing is our scheme is contain a parameter alpha, which is a shape parameter that we see after that have an important roles in the limit curve or surface. So as we proved in our previous work, that this scheme is generate C1 limit curve. And here, as you say, the examples of application of our scheme. So in blue we have a control polygonal, and by application and the same control polygonal our scheme but by changing the values of alpha, we can see that the shape of the limit curve changing from the hyperbolic one to trigonometric one. However, in the case of alpha between 0 strict and 1, we have the mixed between. Now let's moving to bivariate case. We use for the regular case the transfer product, which the matrix of this transfer product is expressed as follow, and the formula is expressed like that. For the irregular versus our scheme matrix can be expressed like that. And in the application of the algorithm, we calculate the new point by application the mask for the regular like that, and for the irregular facet we apply the mask as follow. And we proved that this scheme is generate G1 limit surface. When the proof we used the theorem of Conti, which talking about if we have two subdivisions, the first one is non-stationary and the other one is stationary. But the stationary scheme, it is C1 conversion and the regular vertices, and the contain this factor. Also, the non-stationary contain this factor, and we have the asymptotic equivalent of order 1 between the two cases. And we have this condition, so if the stationary is G1, the non-stationary is also G1. And we applied this, we verify all this condition between our non-stationary scheme proposed and the stationary of the 7 scheme. And for the numerical example, as we say, it's the same thing for the univariate case. So the sweeping of the parameter alpha, fx, and the limit surface. And for alpha 1 we have like sphere or blob, and for alpha equals 0 we have a poloid, and for the other alpha we have the mixed between. So we have different limit surface. For the conclusion, we can say that we had proposed a new surface scheme which mixes between hyperbolic and trigonometric, and which have different limit surface, not like those 7 scheme. It's only one that's repeated. And for the future work, as we said before, that the parameter alpha is changing our fx and the limit curve. So the idea is, why not apply for each age specific values of alpha, which means between p0 and p1 we apply values of alpha 0, between p1 and p2 alpha 1, p1, p2, p3 alpha 2, and p3 and p4 alpha 3. And the result of this application is a new curves that contain different kind of local limit surface, which means it can be contain a trigonometric, a parabolic, polynomial, etc. But our future work is especially is apply this in surface case. And in my bibliography I used all this literature. So thank you for your attention.